Hello viewers, welcome to my channel Online Biology Tutorials. In today's live, we will be reading chapter 9 Gravitation of NCRT class 9 Science. I hope the screen is visible to everybody. Every word is clear on the screen. Let's begin. Let's start. So, we have learned about the motion of objects and forces as the cause of motion. We have learned that a force is needed to change the speed or the direction of motion of an object. We always observe that an object dropped from a height falls towards the earth. We know that all the planets go around the sun. The moon goes around the earth. In all these cases, there must be some force acting on the objects, the planets, and on the moon. Isaac Newton could grasp that the same force is responsible for all these. This force is called the gravitational force. In this chapter, we shall learn about gravitation and the universal law of gravitation. We shall discuss the motion of objects under the influence of gravitational force on the earth. We shall study how the force on the earth. We shall study how the weight of a body varies from place to place. We shall also discuss the conditions for objects to float in liquids. Welcome to my channel. The person who has just joined now. 9.1 Gravitation. We know that the moon goes around the earth. An object, when thrown upwards, reaches a certain height and then falls downwards. It is said that when Newton was sitting under a tree, an apple fell on him. The fall of the apple made Newton started thinking. He thought that if the earth can attract an apple, can it not attract the moon? Is the force the same in both the cases? He conjectured that the same type of force is responsible in both the cases. He argued that at each point of its orbit, the moon falls towards the earth. Instead of going on in a straight line, so it must be attracted by the earth. But we do not really see the moon falling towards the earth. Now, this side of the page will be read. Let us try to understand the motion of the moon by recalling activity 7.11. Activity 9.1. Take a piece of thread, tie a small stone at one end, hold the other end of the thread and whirl it around, round, as shown in figure 9.1. Note the motion of the stone, release the thread. Again, note the direction of motion of the stone. Figure 9.1. A stone describing a circular path with a velocity of constant magnitude. This is written in figure 9.1. Before the thread is released, the stone moves in a circular path with a certain speed and changes direction at every point. The change in direction involves change in velocity or acceleration. The force that causes this acceleration and keeps the body moving along the circular path is acting towards the center. This force is called the centripetal, means central seeking force. We are moving to the next page, and it is page number 101 of your NCERT. In the absence of this force, the stone flies off along a straight line. This straight line will be a tangent to the circular path. So, more to know, a tangent to a circle has been shown. ABC with the circle, a straight line that meets the circle at one or and many one point, and only one point is called a tangent to a circle. So, straight line ABC is a tangent to the circle um, at point B. The motion of the moon around the earth is due to the centripetal force. The centripetal force is provided by the force of attraction of the earth. If there were no such force, the moon would pursue a uniform straight line motion. It is seen that a falling apple is attracted towards the earth. Does the apple attract the earth? If so, we do not see the earth moving towards an apple. Why? According to the third law of motion, the apple does attract the earth, but according to the second law of motion, for a given force, acceleration is inversely proportional to the mass of an object, that is seen in equation 8.4. The mass of an apple is negligibly small compared to that of the earth, so we do not see the earth moving towards the apple. Extend the same argument for why the earth does not move towards the moon. In our solar system, all the planets go around the sun. By arguing the same way, we can say that there exists a force between the sun and the planets. From the above facts, Newton concluded that not only does the earth attract an apple and the moon, but all objects in the universe attract each other. This force of attraction between objects is called the gravitational force. 9.1.1 Universal Law of Gravitation. Every object in the universe attracts every other object with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between them. The force is along the line joining the centers of two objects. So A and B are two objects, distance is d, F is equals to g capital M small m by d square. Figure 9.2 is showing the gravitational force between two uniform objects is directed along the line joining their centers. Let two objects A and B of masses capital M and small m lies at a distance small d from each other as shown in figure 9.2. Let the force of attraction between two objects be capital F. According to the universal law of gravitation, the force between two objects is directly proportional to the product of their masses. That is, F is directly proportional to capital M into small m. And the force between two objects is inversely proportional to the square of the distance between them. That is, F is directly proportional to 1 by d square. Combining equations 10.1 and 10.2. So that means they are talking about the same, right? So here they have 10.1 and 10.2. They are being written because they have not updated it. F is directly proportional to m into small m by d square, or F is equals to capital G capital M small m by d square, where capital G is a constant of proportionality and is called the universal gravitation constant. By multiplying crosswise, equation 9.4 will give you F into d square is equals to G capital M small m. We are flipping. Hello viewers, welcome to my channel. In this video, we will be doing the live reading of chapter 9 from class 9 science book. This is the chapter of NCERT. I have earlier done the live of the previous chapters. In case you are interested in hearing the audio of any of the chapter, you can come to the playlist, and in that playlist from my channel Online Biology Tutorials, you can flip the video of your choice and go ahead. So let's begin the live reading without further ado. So we have learned about the motion of objects and force as the cause of motion. As the cause of motion, we have learned that a force is needed to change the speed or the direction of motion of an object. We always observe that an object dropped from a height falls towards the earth. We know that all the planets go around the sun, the moon goes around the earth. In all these cases, there must be some force acting on the objects, the planets, and on the moon. Isaac Newton could grasp that the same force is responsible for all these. This force is called the gravitational force. In this chapter, we shall learn about gravitation and the universal law of gravitation. We shall discuss the motion of objects under the influence of gravitational force on the earth. We shall study how the weight of a body varies from place to place. We shall also discuss the conditions for objects to float in liquids. So we are done with the first paragraph. In case you are liking the audio, you can hit the like button and share it with your friends. So we are coming to the next heading, 9.1, gravitation. We know that the moon goes around the earth. An object, when thrown upwards, reaches a certain height and then falls downwards. It is said that when Newton was sitting under a tree, an apple fell on him. The fall of the apple made Newton start thinking. He thought that if the earth can attract an apple, can it not attract the moon? Is the force the same in both the cases? He conjectured that the same type of force is responsible in both the cases. He argued that at each point of its orbit, moon falls towards the earth instead of going off in a straight line. So it must be attracted by the earth, but we do not really see the moon falling towards the earth. So we are done with the reading of the left part. We are coming to this part now. Let us try to understand the motion of the moon by recalling activity 7.11. Activity 9.1. Take a piece of thread, tie a small stone at one end, hold the other end of the thread and whirl it round as shown in figure 9.1. Note the motion of the stone. Release the thread. Again, note the direction of motion of the stone. So figure 9.1 is showing you a stone describing a circular path with a velocity of constant magnitude. Let's move on to the next paragraph. Before the thread is released, the stone moves in a circular path with a certain speed and changes direction at every point. The change in direction involves change in velocity or acceleration. The force that causes this acceleration and keeps the body moving along the circular path is acting towards the center. This force is called the centripetal, meaning center seeking force. Next page, please. This side. In the absence of this force, the stone flies off along a straight line. This straight line will be a tangent to a circular path. So the same thing that they have spoken here has been shown here in more to know. So tangent ABC is seen. A straight line that meets the circle at one or only one point is called a tangent to the circle. Straight line ABC is a tangent to the circle at a point B, because at B point it is touching it. The motion of the moon around the earth is due to the centripetal force. The centripetal force is provided by the force of attraction of the earth. If there were no such force, the moon would pursue a uniform straight line motion. It is seen that a falling apple is attracted towards the earth. Does the apple attract the earth? If so, we do not see the earth moving towards an apple. Why? According to the third law of motion, the apple does attract the earth, but according to the second law of motion, for a given force, acceleration is inversely proportional to the mass of an object. That is written in equation 8.4. The mass of an apple is negligibly small compared to that of the earth, so we do not see the earth moving towards the apple. Extend the same argument for why the earth does not move towards the moon. In our solar system, all the planets go around the sun. By arguing the same way, we can say that there exists a force between the sun and the planets. From the above facts, Newton concluded that not only does the earth attract an apple and the moon, but all objects in the universe attract each other. This force of attraction between objects is called the gravitational force. So we are coming to this side now. 9.1.1 Universal Law of Gravitation. Every object in the universe attracts every other object with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between them. The force is along the line joining the centers of two objects. So figure 9.2 is showing the gravitational force between two uniform objects is directed along the line joining their centers. Let two objects A and B of masses capital M and small m lie at a distance small d from each other as shown in figure 9.2. Let the force of attraction between two objects be capital F. According to the universal law of gravitation, the force between two objects is directly proportional to the product of their masses. That is, F is directly proportional to capital M into small m, and the force between two objects is inversely proportional to the square of the distance between them. So that is F is proportional to 1 by d square. Combining both the equations, you will get F is proportional to capital M into small m by d square, or F is equals to capital M small m by d square, where g is the constant of proportionality and is also known as the universal gravitational constant. By multiplying crosswise, your equation will become F into d square is equals to capital G capital M into small m. Next page now. Capital G is equals to FD square capital M into small m. The SI unit of G can be obtained by substituting the units of force, distance, and mass in the above equation, and it will become Newton meter square per kilogram square. The value of G was found out by Henry Cavendish in 1731 to 1810, means these are the years for which he was alive. By using a sensitive balance, the accepted value of capital G is 6.673 into 10 to the power minus 11 Newton meter square per kg square. We note that there exists a force of attraction between the two objects. Compute the value of this force you and your friend sitting close by. Conclude how do you not experience this force. More to know, the law is universal in the sense that it is applicable to all the bodies, whether the bodies are big or small, whether they are celestial or they are terrestrial. Inverse square. Saying that f is inversely proportional to the square of the distance means, for example, that if the d gets bigger by a factor of 6, then f becomes 1 by 36 times smaller. So numerical is given. Example 9.1. The mass of the earth is 6 into 10 to the power 24 kg and that of the moon is 7.4 into 10 to the power 22 kg. If the distance between the earth and the moon is 3.84 into 10 to the power 5 kilometer, calculate the force exerted by the earth on the moon. Take capital G as 6.7 into 10 to the power minus 11 Newton meter square per kg square. The mass of the earth is already given, mass of the moon is given, so the distance between the earth and the moon can be calculated as d is equal to 3.84 into 10 to the power minus 10 to the power 5 kilometer. So here they have converted kilometer into meter, that's why they have multiplied by 1000, so the value becomes 3.84 into 10 to the power 8 meter. Capital G will become 6.7 into 10 to the power minus 11 Newton meter square per kg square. From equation 9.4, the force exerted by the earth on the moon is F is equals to capital G, capital M, small m by d square. So after putting all the values, the value that you will receive is 2.02 into 10 to the power 20 Newton. Thus the force exerted by the earth on the moon is 2.02 into 10 to the power 20 Newton. Questions. Question number 1. State the universal law of gravitation. 2. Write the formula to find the magnitude of the gravitational force between the earth and an object on the surface of the earth. 9.1.2. Importance of the universal law of gravitation. The universal law of gravitation successfully explains several phenomena which were believed to be unconnected. So one was the force that binds us to the earth, the motion of the moon around the earth, the motion of planets around the sun, and the tides due to the moon and the sun. 9.2 Free fall. Let us try to understand the meaning of free fall by performing this activity. Take a stone, throw it upwards, it reaches a certain height and then it starts falling down. We have learned that the earth attracts objects towards it. This is due to the gravitational force. Whenever objects fall towards the earth under their force alone, we say that the objects are in free fall. Is there any, next page, change in the velocity of falling objects? While falling, there is no change in the direction of motion of the objects, but due to the earth's attraction, there will be a change in the, excuse me, magnitude of the velocity. Any change in velocity involves acceleration. Whenever the object falls towards the earth and acceleration is involved. This acceleration is due to the earth's gravitational force. Therefore, this acceleration is called the acceleration due to the gravitational force of the earth or acceleration due to gravity. It is denoted by small g. The unit of small g is the same as that of the acceleration, that is meter per second square. We know from the second law of motion that force is the product of mass and acceleration. Let the mass of the stone in activity 9.2 is m. we already know that there we already know that there is acceleration involved in falling objects due to the gravitational force and is denoted by small g. Therefore, the magnitude of the gravitational force F will be equal to the product of mass and acceleration due to the gravitational force, that is F is equals to mg. From equation 9.4 to 9.6, we have mg is equals to g capital M small m d square, or G small g is equals to capital M by d square, where m is the mass of the earth, small d is the distance between the object and the earth, Let an object be on or near the surface of the earth. The distance d in equation 9.7 will be equal to capital R, the radius of the earth. Thus, for objects on or near the surface of the earth, mg is equals to capital G, capital M by r square. Small g is equals to capital G, M by r square. The earth is not a perfect sphere. As the radius of the earth increases from the poles to the equator, the value of g becomes greater at the poles than at equator. For most of the calculations, we can take small g be more or less constant on or near the earth. But for objects far from the earth, the acceleration due to gravitational force of earth is given by equation 9.7. So 9.2.1, to calculate the value of small g. To calculate the value of small g, we should put the values of capital G, capital M and R in equation 9.9, namely universal gravitational constant. So capital G is equal to 6.7 into 10 to the power minus 11 Newton meter square per kg square. Mass of the earth capital M is equal to 6 into 10 to the power 24 kg, and radius of the earth is R is equal to 6.4 into 10 to the power 6 meter. So small g is equals to capital G, capital M upon R square. Placing the values, you'll get 9.8 meter per second square. Thus, the value of acceleration due to gravity of the earth is denoted by small g is equals to 9.8 meter per second square. I request you that whenever you will be hearing the audio of this gravitation chapter, don't forget to share it with your friends. 9.2.2, Motion of objects under the influence of gravitational force of the earth. Let us do an activity to understand whether all the objects, hollow or solid, big or small, while fall from a height at the same rate. Activity 9.3, take a sheet of paper and a stone, drop them simultaneously from the first floor of a building. Observe whether both of them reach the ground simultaneously. We see that paper reaches the ground little later than the stone. This happens because of the air resistance. The air offers resistance due to the friction to the motion of the following objects. The resistance offered by air to the paper is more than the resistance offered to the stone. If we do the experiment in a glass jar from which air has been sucked out, the paper and the stone will fall at the same rate. Let's come to the next page, that is page number 104 of your NCERT. We know that an object experiences acceleration during free fall. From equation 9.9, this acceleration experienced by an object is independent of its mass. This means that all objects, hollow or solid, big or small, should fall at the same rate. According to a theory, Galileo dropped different objects from the top of the Leaning Tower of Pisa in Italy to prove the same. As g is constant near the earth, all the equations for the uniformly accelerated motion of objects become valid. With acceleration a replaced by g, the equations are v is equals to u plus at, s is equals to ut plus half at square, v square is equals to u square plus 2s, where u and v are the initial and the final velocity, and s is the distance covered in time t. In applying these equations, we will take the acceleration a to be positive when it is in the direction of the velocity, that is in the direction of the motion. The acceleration a will be taken as negative when it opposes the motion. Example 9.2, a car falls off a ledge and drops to the ground in zero point 0.5 second. Let g is equals to 10 meter per second square for simplifying the calculations. What is the speed on striking the ground? What is its average speed during zero point 0.5 second? How high is the ledge from the ground? Solution: time is equals to half second. Initial velocity is equals to 0 meter per second. Acceleration due to gravity is 10 meter per second square. Acceleration of the car is 10 meter per second square downward. That's it is positive. Speed is equals to v is equals to 80. So v can be calculated as by putting the values. It will become 5 meter per second. Average speed will be equal to u plus v by 2. So after putting the values, you'll get 2.5 meter per second. So distance traveled is s is equals to half by 80 square. Putting the values, you'll get 1.25 meter. That's its speed on striking the ground is 5 meter per second. Its average speed during the zero point 0.5 second is 2.5 meter per second. Height of the ledge from the ground is 1.25 meter. Example 9.3, an object is thrown vertically upwards and rises to a height of 10 meter. Calculate the velocity with which the object was thrown upward and the time taken by the object to reach the highest point. So distance traveled is 10 meter. Final velocity is 0 meter per second. Acceleration due to gravity is 9.8 meter per second square. Acceleration of the object A is equals to minus 9.8, as it is going upward against the direction of gravity. That is why the sign will be minus 9.8. So to calculate the initial velocity, we will be using the formula v square is equals to u square plus 2s. So after putting the values, you will get u is equals to 14 meter per second. V is equals to u plus 80. So initial velocity we have already calculated here. Final we have calculated here. So by this you can calculate t is equals to 1.43 second. Thus initial velocity is 14 meter per second and time taken is 1.43 second. So the in-text questions on this page are two. Question number one, what do you mean by free fall? Second, what do you mean by acceleration due to gravity? Next page. So we are left with this page 1, 2, 3, 4, 5, and then we will be ending this page. Right? So we were done till here. We are on 9.3 mass. We have learned in the previous chapter that the mass of an object is the measure of its inertia. We have also learned that greater the mass, the greater is its inertia. It remains the same whether the object is on the earth, the moon, or even in outer space. Thus, the mass of an object is constant and does not change from place to place. 9.4 weight. We know that the earth attracts every object with a certain force, and this force depends on the mass m of the object and the acceleration due to gravity g. The weight of an object is the force with which it is attracted towards the earth. We know that F is equals to ma, that is F is equals to mg. Hi, the one who has joined right now, that is F is equals to mg. The force of attraction of the earth on an object is known as the weight of the object. It is denoted by W. Substituting the same in equation 9.14, we have W is equals to mg. As the weight of an object is the force with which it is attracted towards the earth. The SI unit of weight is the same as that of the force, that is Newton, denoted by capital N. The weight of is a force acting vertically downward, so it has both magnitude and direction. So we have learned that the value of g is constant at a given place. Therefore, at a given place, the weight of an object is directly proportional to the mass, saying m of the object. That is, w is directly proportional to m. It is due to this reason that at a given place, we can use the weight of an object as a measure of its mass. The mass of an object remains the same everywhere. That is on the earth and on any planet where its weight depends on its location, because g depends upon the location. So we come on to 9.4.1, weight of an object on the moon. We have learned that the weight of an object on the earth is the force with which the earth attracts the object. In the same way, the weight of an object on the moon is the force with which the moon attracts the object. The mass of the moon is less than that of the earth. Due to this, the moon exerts lesser force of attraction on objects. Let the mass of an object be m, let its weight on the moon be wm, let the mass of the moon be mm, and its radius is rm. By applying the universal law of gravitation, the weight of the object on the moon will be wm is equals to capital G, capital M, small m into small m, r square m. Let the weight of the same object on the earth be we. The mass of the earth is capital M and its radius is r. So table 9.1 is showing you the mass and radius of the celestial body earth and moon, and these are to be learned. So the mass of the earth is 5 into 95.98 into 10 to the power 24 kg, and the mass of the moon is 7.36 into 10 to the power 22 kg, whereas the radius in is given in the meter, so it is 6.37 into 10 to the power 6 for earth and 1.74 into 10 to the power 6 for moon. From equations 9.9 and 9.15, we have W is equals to G, capital M, small m, r square. Substituting the values, you will get the value as WE is equals to 1.4 10 to the power 11 capital G into small m. Dividing both the equations, we'll get Wm by We is equals to 0.165, that is equals to 1 by 6. That is weight of the object on the moon to the weight of the object on the earth is 1 by 6. So same is written here, weight of the object on the moon is equals to 1 by 6 the weight of the on the earth. The students who are just watching this live of the gravitation chapter, in case you are liking the audio, please don't forget to hit the like button. For class 9 students, I have also recorded the complete explanation of the fundamental unit of life. You can visit my channel and go to the playlist. I have also done the recording of the previous chapters. You can check the other audios as well in my playlist. So come on to page number 106 of your NCERT. Example 9.4, mass of an object is 10 kg. What is its weight on the earth? Solution, mass is 10 kg. Acceleration due to gravity is 9.8 meter per second square. So W is equals to m into g. W will become 98 Newton. Thus the weight of the object is 98 Newton. Example 9.5, an object weighs 10 Newton when measured on the surface of the earth. What would be its weight when measured on the surface of the moon? Solution, we know weight of object on the moon is 1 by 6 to the weight on the earth, that is Wm is equals to We by 6, 10 by 6 Newton. So it will become 1.67 Newton. Thus the weight of an object on the surface of the moon would be 1.67 Newton. In text questions are two. Question number 1 is, what are the differences between the mass of an object and its weight? Question number 2, why is the weight of an object on moon is 1/6 its weight on the earth? 9.5, pressure. Have you ever wondered why a camel can run in a desert easily? Why an army tank weighing more than 1,000 tons rests upon a continuous chain? Why a truck or a motor bus has much wider tires? Why cutting tools have sharp edges? In order to address these questions and to understand the phenomenon involved, it helps to introduce the concepts of the net force in a particular direction called thrust and the force per unit area pressure acting on the object concerned. Let us try to understand the meanings of thrust and pressure by considering the following situations. Situation 1, you wish to fix a poster on a bulletin board as shown in figure 9.3. To do this task, you will have to press drawing pins with your thumb. You apply a force on the surface area of the head of the pin. This force is directed perpendicular to the surface area of the board. This force acts on a smaller area at the tip of the pin. So same thing has been written here along with the figure 9.3. To fix a poster, drawing pins are pressed with the thumb perpendicular to the board. Situation 2, you stand on loose sand. Your feet go deep into the sand. Now lie down on the sand. You will find that your body will not go that deep in the sand. In both the cases, the force exerted on the sand is the weight of your body. Let's move to the next page, that is page number 107 of your NCRT. You have learned that weight is the force acting vertically downwards. Here, the force is acting perpendicular to the surface of the sand. The force acting on an object perpendicular to the surface is called thrust. When you stand on loose sand, the force, that is the weight of your body, is acting on an area equal to the area of your feet. When you lie down, the same force acts on an area equal to the constant area of your whole body, which is larger than the area of your feet. Thus, the effects of forces of the same magnitude on different areas are different. In the above cases, thrust is the same, but effects are different. Therefore, the effect of thrust depends on the area on which it acts. The effect of thrust on sand is larger while standing than while lying. The thrust on unit area is called pressure. Thus, pressure is written as thrust divided by area. Substituting the SI unit of thrust and area in equation 9.20, we get SI unit of pressure as N upon meter square or M minus 2. In honor of scientist Blaise Pascal, the SI unit of pressure is Pascal, denoted as PA. Let us consider a numerical example to understand the effects of thirst acting on different areas. Example 9.6. A block of wood is kept on the tabletop. The mass of wooden block is 5 kg and its dimensions are 40 into 20 into 10 centimeter. Find the pressure exerted by the wooden block on the tabletop if it is made to lie on the tabletop with its side of dimensions A 20 into 10 centimeter, B 40 into 20 centimeter. So the solution is given here. The mass of the wooden block is 5 kg. The dimensions are already given 40 into 20 into 10. Here the weight of the wooden block applies a thrust on the tabletop. That is, the thrust will be F is equals to mg. So force will become 49 Newton. Area of the side will be length into breadth. So it will become 0.02 meter square. From equation 9.20, pressure is equals to thrust upon area. So putting the values, we get pressure as 2450 Newton per meter square. When the block lies on its side of the dimensions 40 into 20 centimeter, it exerts the same thrust. So area is equals to length into breadth. That will become 0.08 meter square. From equation 9.20, pressure is equals to 49 upon 0.08 meter square. So pressure will become 612.5 Newton per meter square. The pressure exerted by the side 20 centimeter into 10 centimeter is 2450 Newton per meter square, and by the side 40 into 20 centimeter is 612.5 Newton per meter square. Thus the same force acting on a smaller area exerts a larger pressure and a smaller pressure on a larger area. This is the reason why a nail has a pinned or pointed top, knives have sharp edges, and buildings have wide foundations. 9.5.1 Pressure in fluids. All liquids and gases are fluids. A solid exerts a pressure on a surface due to its weight. Similarly, fluids have weight and they also. Let's move to the next page. That is page number 108 of your NCERT. Exert pressure on the base and the walls of the container in which they are enclosed. Pressure exerted in any confined mass of fluid is transmitted undiminished in all the directions. Buoyancy 9.5.2. Have you ever had a swim in a pool and felt lighter? Have you ever drawn water from the well and felt that the bucket of water is heavier when it is out of the water? Have you ever wondered why a ship made of iron and steel does not sink in the sea water, but while the same amount of iron and steel in the form of a sheet would these questions can be answered by taking buoyancy in consideration. Let us understand the meaning of buoyancy by doing an activity. So we are starting with the reading of the activity 9.4. Take an empty plastic bottle, close the mouth of the bottle with an airtight stopper, but put it in a bucket filled with water. You see that the bottle floats. Push the bottle into the water. You feel an upward push. Try to push it further down. You will find it difficult to push deeper and deeper. This indicates that water exerts a force on the bottle in the upward direction. The upward force exerted by the water does goes on increasing as the bottle is pushed deeper till it is completely immersed. Now release the bottle, it bounces back to the surface. Does the force due to the gravitational attraction of the earth act on this bottle? If so, why doesn't the bottle stay immersed in water after it is released? How can you immerse the bottle in water? The force due to the gravitational attraction of the earth act on the bottle in the downward direction. So the bottle is pulled downwards, but the water exerts an upward force on the bottle. Thus, the bottle is pushed upwards. We have learned that weight of an object is the force due to gravitational attraction of the earth. When the bottle is immersed, the upward force exerted by the water on the bottle is greater than its weight. Therefore, it rises up when released. To keep the bottle completely immersed, the upward force on the bottle due to water must be balanced. This can be achieved by an externally applied force acting downward. This force must at least be equal to the difference between the upward force and the weight of the bottle. The upward force exerted by the water on the bottle is known as upthrust or buoyant force. In fact, all objects experience a force of buoyancy when they are immersed in a fluid. The magnitude of this buoyant force depends on the density of the fluid. Let's move on to the next topic 9.5.3, why objects float or sink when placed on the surface of a water. Let us do the following activities to arrive at an answer for the above question. Take a beaker filled with water, take an iron nail and place it on the surface of the water. Observe what happens. The nail sinks. The force due to the gravitational attraction of the earth on the iron nail pulls it downward. This is an upthrust of water on the nail, which pushes it upwards, but the downward force acting on the nail is greater than the upthrust of water on the nail, so it sinks. Figure 9.5, an iron nail sinks and a cork floats when placed on the surface of water. So we are moving to page number 109, activity 9.6. Take a beaker filled with water, take a piece of cork and an iron nail of equal mass, place them on the surface of water and observe what happens. The cork floats while the nail sinks. This happens because of the difference in their densities. The density of a substance is defined as the mass per unit volume. The density of cork is less than the density of water. This means that the upthrust of water on the cork is greater than the weight of the cork, so it floats. Figure 9.5. The density of an iron nail is more than the density of the water. This means that the upthrust of water on the iron nail is less than the weight of a nail, so it sinks. Therefore, objects of density lesser than that of the liquid float on the liquid. The objects of density greater than that of a liquid sink in the liquid. Questions 1. Why is it difficult to hold a school bag having a strap made of a thin and strong string? 2. What do you mean by buoyancy? 3. Why does an object float or sink when placed on the surface of water? 9.6 Archimedes principle. Activity 9.7. Take a piece of stone and tie it one end of a rubber string or a spring balance. Suspend the stone by holding the balance or the string as shown in figure 9.6. Note the elongation of the string and the reading of the spring balance due to the weight of the stone. Now, slowly dip the stone in the water in a container as shown in figure 9.